Alright, hello and welcome back. Alright, in this next lesson, suddenly our inequalities aren't so simple anymore. I accidentally left out the word linear here. They're still going to be linear for now, but they're going to be something called compound inequalities. And so the goals are to be able to talk about the graph of a compound inequality using the words and or. And then we're going to graph compound inequalities, and we're going to solve compound inequalities to create the graph, so on and so forth. We actually have to start with an English lesson this time. So in English class, a simple sentence expresses a complete thought, so therefore probably has to have a subject and a verb. And so here are two simple sentences. Joe was waiting for the train. The train was late. And one of the things you do in English is you learn to revise your work. So instead of these two simple sentences, let's make this a little more interesting for the reader and create what's called a compound sentence, which joins two related simple sentences using a connecting word called a conjunction. And, but, because, or, yet. There are a few others. And so same basic thought as these two sentences, but as a compound sentence. Joe was waiting for the train because it was late. So if that's how simple sentences get combined to make compound sentences, you might be thinking correctly that we're going to combine simple inequalities to get compound inequalities. And sure enough, compound inequalities are two simple inequalities glued together with the word and or the word or. Those are the only two conjunctions we're going to use. Okay. And means both inequalities must be true at the same time, and so and's usually going to be between this. X is between two numbers. The word or indicates that only one of the inequalities needs to be true at a time, and in most cases it's impossible for both to be true at the same time. So let's just look at a quick example here. Describe each inequality in words, then draw a number line graph. Okay, so t is between, so we're going to need the word and. So t is, let's see, 0 is less than t, so t is greater than 0, and, let's see, t is less than or equal to 1, is how you would read this in words. T is greater than or equal to 0, and less than or equal to 1. And I'll be honest with you, a lot of people just cheat and say that t is between 0 and 1, including the 1, but not including the 0. So that would be inclusive on the 1, exclusive on the 0, exclusive, inclusive, because of the or equal to. This one on your notes you would read is a lot more straightforward. X is less than negative 3, or x is greater than 5. What would these look like as number line graphs? Well, from the previous lesson, a simple inequality looked like a ray. Turns out that the idea of betweenness, an and compound inequality, is going to look like a segment. The or is going to look like two rays pointing in opposite directions. So this sort of gives you the idea. And so let's go back. Ooh, that's still left there from the last lesson. So we've got an inequality that looks like this. 0 is less than t, and t is less than or equal to 1. So our number line graph, let's see, negative 1, 0, 1, 2. We have an open endpoint at 0. We have a closed endpoint at 1. And t is any of these numbers in between. So t could be 0.5 or 7/8 or 0.000137. Doesn't really matter. Let's see, it'd be pi over 4 would definitely be between 0 and 1. So t could be a lot of different things. Our other inequality, x is less than -3, or x is greater than 5. Number line graph. Let's see. Let's count by twos. It's kind of cheap. Let's put 0 right in the middle. 0, 2, 4, 6, 8. Pretend that scales, accurate. -2, -4, -6. So what would we have? Well, we would have an open endpoint at -3, and pointing to the left, an open endpoint at 5, pointing to the right. And again, technically these number line graphs should be down on the number line, but I'm trying to draw them in such a way that it's easier for you to see, which I'll also do on the board, and anytime I draw them on paper for you all. So basically, anytime you see me draw them, I'll be drawing them wrong because they'll be floating up here, but oh well. A couple more complicated words that go with this lesson are intersection and union. This might remind you of like your Venn diagram days, which we'll get back into this actually in just a couple lessons. The intersection of two sets of numbers contains or includes any number that's in both sets. So it's the overlap, or what's in common. Think about the intersection of two roads. It's where they cross. An and compound inequality is actually an example of intersection. What I mean by that is the way an and inequality works is you have the number line, and say some part of the inequality does this, and some part of the inequality does this. Then the and inequality, the official answer, will do this. Because it's pretty clear that red and blue make purple, and that's the overlap is in between them. When I've taught like pre-algebra, algebra 1 type classes in the past, I've even had people draw them like this for the first day, but you all probably won't have to do that. But if it makes you feel better and it helps you understand it, go for it. So that's kind of where this picture comes from. It's the overlap of two rays that are pointing in opposite directions. A union of two sets is, well, union's like joining or together. So it's anything that's in any of the two sets is part of the union of the two sets. And an or inequality is an example of a union. It's this thing or this thing, and they're glued together even though they're not actually touching. Alright, a replacement set includes values of the variable that should be considered as possible solutions in a given context, and these are usually intended to be guess and check type problems. Okay, so here's our replacement set. We're just going to guess and check, get a feel for a problem. We'll start in the middle and work our way out. 0. Okay, so let's see. We're going to try these numbers. We're going to start with 0. We're going to try them for x right here. And we want to know whether each one is going to work, which is fancy, or not as fancy way of saying that when you put the 0 in for x, you get a true statement. Well, 3 halves of 0 is still 0. 0 plus 1 is 1. And so if x is 0, we get the statement -2 is less than or equal to 1 is less than 7, which is a true statement. So 0 works. Good job, 0. Alright, let's try 1, positive 1. 3 halves times 1. Well, 3 halves times 1 is 3 halves. If you don't like fractions very much, excuse me, you might remember that 3 halves, you still might remember that 3 halves is 1.5. And 1.5 plus 1 is 2.5. So if x happens to be 1, you get -2 is less than or equal to 2.5, which is less than 7. And that's also true. Well, let's try -1. Instead of 1.5, we get -1.5, and -1.5 plus 1 would be -0.5. So if you try x being -1, excuse me, this is going to have to be the last one for tonight. Get -2 is less than or equal to -1.5 plus 1 would be -0.5. So less than 7. Okay, that's a true statement. Good job, us. We checked 3 and they're all true. Alright, from there, let's see if we can just kind of check them out loud together. And I'm going to check them in purple, I guess. Just so that we remember that the ones that are in purple I'm not actually showing you the work for. You could think about it, show it if you need to. 3 halves times -2. The 2's cancel, and 3 times, excuse me, a -1's -3, and -3 plus 1 is -2, and -2 would be less than or equal to -2 and less than 7. So it worked, but barely. And so let's see. Let's just make this a little quick. When we put x in, let's just label it in and out. So we're putting x values in and some values coming out, and we put in -2. We got -2, so it checked because it was between -2 and 7 like it's supposed to be. Well, we try -3, and 3 halves of -3, so -4.5 plus what's -3.5, excuse me. Excuse me, I believe that's the case. And that's not correct. It's not on the correct side of -2. It's not going to be between -2 and 7. So -3 didn't work. Now what you're kind of supposed to realize, well, if -3 doesn't work, -4 and -5 probably don't stand a chance. And it is the case. I'll let you check those yourself if you like. Let's go to the other end. Let's check 2. 3 halves times 2 would cancel down to just 3. 3 plus 1 is 4. Good job, 2. Let's check 3. 3 halves times 3 would be 9 halves is 4.5 plus 1 is 5.5. 5.5 is between -2 and 7. Good job, 3. You worked. Let's check 4. 3 halves of 4. Well, the 2 cancels the 4 to 2. 3 times 2 is 6. 6 plus 1 is 7. 7 is equal to 7, not less than 7. So 4 doesn't work. And if 4 doesn't work, 5 doesn't stand a chance. I'll let you check it for yourself. Oh, so look at that. We had this nice little idea that the part with the x was between the -2 and the 7, and then the numbers that worked basically were -2, -1, 0, 1, 2, 3, 4. And so at this point, if I said add one number to this set that will definitely work, I bet most of you would know to start picking something between -2 and 3. And a couple of you might get a little like reckless or just want to be curious and know, and you might check like -2.5 or 3.5 or 3.8 or -2.1, trying to figure out exactly when these numbers start and stop working. And that's sort of the idea of these compound inequalities. When we're going to actually solve them, it's going to be kind of like solving two inequalities at the same time. You can, I wouldn't say will, that's a little too strong. You can separate it into two inequalities and solve each and then put them back together. I think for you all that's not going to be necessary. We'll do it both ways. And then we got to make sure to include a number line graph. And that's it for the notes. I have the examples right here. Here we go. Switch back to blue. Let's see. We would subtract 3 on both sides. X is less than 2. Or, let's see, add 1. 2x is greater than or equal to 10. Divide by 2 on both sides. X is greater than or equal to 5. So there's our solution. X is less than 2. Or greater than or equal to 5. 1, 2, 3, 4, 5, 6, 7. Let's see, x is less than 2 would be open pointing left, or greater than or equal to 5 would be closed and pointing right. And again, try to keep in mind that an and comes together and the ors point apart. Okay, so that's definitely an or, so we should be good. Let's see, here we would subtract 2, get x is less than 3. Or, let's see, we would divide by 3 and get x is greater than or equal to 6. And we would need to create a graph. 2, 3, 4, 5, 6, 7. Let's see, an open endpoint at 3 pointing left, a closed endpoint at 6 pointing right. So, kind of two similar problems just to get us warmed up. Alright. Well, these are a little more interesting looking. Here we go. Add 1 to get 8. 2x is greater than 8. Divide by 2. X is greater than 4. See, here we would subtract 1. 4 minus 1 is 3. Divide by -3, so x is, let's see, -1. We got to reverse. So here's our or. X is greater than 4 or less than -1. See, I'd probably count with 2's. I was being lazy here. Let's see, we would have an open endpoint at 4 pointing right. We would have an open endpoint at -1 pointing left. So even if these are on kind of flip-flop sides, the picture still looks like an or. It's pointing away. If it really bothers you, you could rewrite it, and this wouldn't cause you to flip any inequalities, so that it matches sort of the numbering on the number line. Alright, let's see, we subtract 7, x is greater than -9. Oh wait, this one says and. That might make a difference, because we're kind of expecting it to come together if we get an and. We subtract 5, negative 2x greater than, subtract 5 is 15. Half of 15 is 7.5. But we divided by negative, so it's negative 7.5, and we would need to reverse inequality. So x is less than negative 7.5. So here's our and number line picture. Let's see, negative 10, negative 9, negative 8, negative 7, that's a negative 7, negative 6, it's a terrible negative 7, but there you go. Alright, so let's see, we have x is greater than negative 9, so be open at negative 9 pointing right, but at x is less than negative 7.5, it would be open pointing left. What's going to happen with the blue and the red? They are going to come together and make purple. There's our little and inequality. Some of you might like writing it with the x in the middle at this point. That would be an option. Alright. Ooh, how does this look different? Well, one, that's just two copies of the same problem. So that means we're going to work this one two ways. The x is in between. So one strategy is to work the problem as two parts. So you say, well, negative 3 is less than or equal to 6x minus 1. You would add 1 on both sides, which would bump that up to negative 2. Divide by negative 6. We don't need to reverse inequality because it was positive that we divided by it. Just the answer that was negative. All that reduces to negative 1/3. And then some of you might be tempted to turn that around, but just kind of bear with me for a second. But that was just half the problem. Here's the other half. 6x minus 1 is also less than 3. So we could solve that. And 6x minus 1 less than 3. Add 1, 6x less than 4. Divide by 6, x less than 4/6. Which we should know reduces to 2/3. Pin not working. There it goes. And so then you kind of put it back together. You say, okay, well, negative 1/3. Let's do that in purple. Negative 1/3 less than or equal to x. And x is less than or equal. Excuse me. And x is less than 2/3. Different way. We should be able to kind of do this all at once. Instead of doing something on two sides, we've got to do all three parts, and we've got to move things out of the middle. And so we look at the middle and we say, well, we would normally add 1 here. But what ends up happening is people who kind of know what they're doing but do this wrong, they just add 1 right here. So this thing's got 3 parts, not 2 sides. So to keep it balanced, you have to add 1 on all 3 parts. So it'd be negative 2 less than or equal to 6x less than 4. We want x by itself, so we need to undo that multiplication. So we divide each piece by 6 all the way through. And in my opinion, with a lot less work. you have that x is between those two fractions in order for this inequality to be true. Again, I think that's a lot less work, so I have a feeling a lot of you will prefer it. Just make sure that whatever you do to all three parts, okay? Oh yeah, number line graph. These are both fractions with denominators of thirds. So here we go, -1, 0, 1, 2. We want to be between -1/3 and 2/3, and they're both closed, and x is any number between those. So you would connect it and make a segment. Excuse me. Here we go. Last one. Oh my, I bet you're really disliking this one, because not only is it the in-between business, but it's also a fraction. We hate fractions, so we're going to fraction bust. That means we now need to multiply both sides by 5. So 15 is less than or equal to, the 5's cancel, so x minus 2. Oh, and then now we just need to add 2 to get x by itself. And oh my, how could we do that on the number line? I'm going to cheat bad. I'm going to start at 15 and count my 5s. 15, 20, 25, 30, 35. 17's about right there. Why's my pen not working right? There's 17. 32 is about right there. And it's an and, the x is in between. So on this one, again, it was 3 parts. We had to fraction bust with all 3 parts to get started, but after that it wasn't too bad. Hopefully you'll agree that these weren't too bad. They really were just sort of taking all the equation stuff, putting it together with this added wrinkle that you might have 3 parts, or you might have 2 separate pieces you have to work with. Like this problem, you could have done this as 2 separate pieces if you liked. That's it for the show. This one also was a little longer than I had planned on, but it will be alright. If you have questions and stuff, you need to definitely ask in class, because it is easy to make mistakes and it is easy to get lost and not be sure you're completely understanding what's going on. Thank you for your time. I will talk to you later. Bye.